Hey y'all, this is Angie with Angie's Beyond the Lecture. This is the first section of our review problems on the chemistry final exam review. And again, we're in the foundations of chemistry, so we're in the first, I would say, 6 weeks or so of chemistry, just reviewing general concepts. It's quite honestly not the most exciting. It's not a lot of, we're not getting into chemical equations yet or naming, putting the formulas together. It's simply the basics here. And I have a 50 problem practice exam put together. We'll go over the answers here and hopefully solidify your knowledge in this particular section before you move on to progress in the semester and continue the semester review, of course, because we do have finals coming up in the coming weeks. And at that, we'll start off with the first question. This asks or says, chemistry is the scientific study of blank and the blank it undergoes. So if we go back to the beginning of your notes, we do talk about chemistry there and what it actually studies. And I'll go ahead and put in the answers. I mean, people can easily, you'll go back to your notes and or go to word bank or however for these fill in the blank questions. But basically, chemistry is a scientific study of matter and the changes that the matter undergoes. So matter, I'll just stick that right there below. And then changes. Okay. Chemistry, again, is a scientific study of matter and the changes it undergoes. Now, the next question, I forgot I actually did duplicate questions here, but we'll go ahead and keep up with the fill in the blanks here in this first part. The branch of science most concerned with the composition and behavior of substance is called, well, what are we studying? Chemistry, right? Boom. There we go. So there's another classic definition. Again, this is simply going back and reviewing the basics. You may see a multiple choice or fill in the blank question. Who knows? I've seen it before. So just, again, reviewing the common terminology. The physical stuff that makes up everything around us is known as, well, any guesses? I realize that's rhetorical because no one can chime in, but the simple answer would be matter. Matter, okay? So matter is anything that basically takes up space, okay? Has mass and takes up space. So that's from the first section that I went over, basically the definition of chemistry, and I think I added on some practical uses in everyday life and various sectors of our world. We'll get into, after this particular part, we'll get into some more common questions you're going to see. Thought I'd start you off easy and kind of work our way into some multiple choice and free answer and things like that. But I'll probably take over with the pen here so I can write. I'll be using my keyboard and the pen as needed. So the fourth question here says, which of the following is a physical property? So again, we need to look at these options. There are four. Which one fits the bill? And the other ones we can kick out, right? We have A as flammability, B is reactivity with oxygen, C is melting point, D is the ability to decompose. So when I look at A, B, and D, A, B, and D, those are all similar. Those all point to chemical reactions. And this was discussed in the video in that section. Flammability is definitely a chemical property and definitely an indicator of a reaction that might take place. We also have reactivity with oxygen. So things that can react with oxygen and create new products, that would be chemical as well. And the ability to decompose or break down, that's chemical as well. You know, in A, B, and D, we're essentially changing or looking at the possibility of a particular substance changing based on what it interacts with, either flame, heat, oxygen, or simply breaking down. So what we're looking at is A, B, and D. are clearly going to be non-answers, right? And C, melting point, that does fit the bill. Melting point, boiling point, those are key physical properties. Melting point takes you from a solid to a liquid, and then boiling point starts the process of moving a substance from liquid to gas. Okay, physical property. Remember, physical properties do involve melting point and boiling point. Okay, on to the next question. Which of these describes a chemical property? Our options are A, density, B, boiling point, C, color, and D, flammability. Okay, chemical. So when I see chemical right here, that's a keyword, chemical. That means I'm looking for reactivity. And A, B, and C, they all indicate physical properties. We just talked about melting point in the previous problem. Boiling point's the same. Color is just something that's physical. It doesn't point to any type of reactivity. And density as well. Density is mass per unit volume, and it describes the physical property of density, or how closely solids are packed. Usually. We can talk about density with liquid and gases as well. But back to our final answer here. A, B, and C, those are physical, right? So I'll just put PPP there, maybe to help out. But D, that's going to be your chemical property. Next up, we have, what is the best clue that a chemical change has occurred? And they give us the options of melting, boiling, formation of a precipitate, or dissolving sugar in water. Okay. Well, melting and boiling, we know those are physical changes, physical processes. Okay. Continuing on to the next question here, we have, what is the best clue that a chemical change has occurred? And we're given the options of melting for A, boiling for B, formation of a precipitate, C, and then dissolving sugar in water. So you can probably see the trend here that 3 of these are going to be physical changes or physical properties, and one of them will be indicate a chemical change. So if we go through step by step, melting and boiling, those are physical changes and rely on physical properties or changes between those properties. Melting is essentially taking solid water to liquid water, right? As an example, right? Taking something that's in solid form and putting it into liquid form by adding heat and changing the state of matter, but not the actual chemical composition. That's the bottom line there. Now, B, boiling, that's similar to melting. Boiling is the process that actually moves liquids over to gases. And formation of a precipitate, that actually looks pretty good. I think we should check that off and look further. D, dissolving sugar into water, that's actually a physical change. If we take sugar into water and dissolve it, it's still sugar, right? It's just hydrated by the surrounding water molecules and dissolved. So we're actually not changing the sugar substance at all. It's still there. We just can't see it any longer. Back to C. C was actually discussed a little bit in the video when we talked about states. Yeah, when we talked about physical and chemical changes. And when we see a precipitate form that wasn't there before, typically it's seen when we combine 2 aqueous solutions, typically solutions that involve water and some type of dissolved salt, and the ions that are formed in these solutions actually find each other, certain ions too. It's just certain ions that meet together, and they don't stay dissolved. They form a solid. And that is discussed more in solution chemistry, but formation of a precipitate is definitely a hallmark of something, a chemical reaction or a chemical change that has been done. So melting, boiling, dissolving, these are all P, right? Physical changes, but C would be your final answer there, formation of a precipitate. It's definitely a hallmark of a chemical change. The next question asks, which of the following is an intensive property? So if you remember intensive is independent. I just remember the IN from intensive matches independent of the amount of substance that you're discussing or looking at. So mass would of course depend on amount of substance. Volume would definitely depend on amount of substance. Density, let's look at that one. If we look at D, length definitely depends on amount. Mass, volume, and length all depend on amount and are extensive properties. By default, C is the correct answer, but just know that density is intensive. So to break it down further, if you were to take like a rock, and we assume it has density that's uniform or same throughout, if you take a little piece of the rock on one side and a little piece of rock on the other side, right? Just maybe take a little piece off each side, it's still going to have the same density. It's still going to have the same mass per unit volume, whether you take, a large piece of that rock off or a small piece, okay? So amount does not matter as long, and we make the reasonable assumption that whatever substance you're looking at, it's the density is uniform throughout or the same throughout. There aren't any major changes. So bottom line is C, density is one of the four listed that is intensive and not extensive. If we look at extensive here, so they could ask you on a test, perhaps flip it around and say, okay, which of these is extensive? And looking at the four options here, we have odor, color, hardness, or mass. And just knowing that extensive follows the extent or depends on the extent of material you have to go with mass, right? Odor depends on the scent, right? Color, that's a physical property. Hardness, that's another physical property. So you'd have to go with mass here. Mass is your final answer for that particular question, which has definite volume but no definite shape. What state of matter has definite volume but no definite shape? We know based on our definitions of solid, liquid, gas. Now plasma, I forgot I threw in plasma here. Plasma is actually what's considered the fourth state of matter. We don't really study it intensively in our high school or maybe even general chemistry. In fact, I only found it noted once in my Gen Chem book. And technically, plasma is defined as atoms that are stripped of their electrons at high temperatures, which results in a gaseous plasma. And it's basically a neutral mixture of positive nuclei and electrons. So what the heck does that mean, right? Bottom line, it's just a superheated ionized gas. And yes, it could be a state of matter. Again, not one we study intensely. This particular definition was in the nuclear reaction section of our chemistry book. So not one I don't think you really need to be familiar with the definition or examples. Again, it's nuclear chemistry and something you don't study very much. So it has to be solid, liquid, or gas. And if we're looking at definite volume but no definite shape, we know solid does have definite volume. It does have definite shape, so it's not solid. And we know gas doesn't have a definite volume. Or yeah, we can measure the volume, but we know it definitely doesn't have a definite shape. It's not like a solid. All the molecules are moving around in random directions. And yes, indeed, we don't have a definite shape on gas. So it has to be liquid. That again is just knowing the definitions of your states of matter. And again, I apologize. I should have put that in. There it is. So this question asks, which mixture scatters light due to the Tyndall effect? So remember, Tyndall effect is where you shine light on a particular mixture, and if it scatters the light, it doesn't just shine right through. It'll scatter the light distinctly, and you can tell what type of mixture it is. So right out off the bat, we can practice our elimination tactics here. We have options A through D, and we have two, like I know right away, they're not part of the mixture pile. I'm expecting to see either a colloid, a solution, or a suspension, those three. And so right away, I know to eliminate. So C and D, sorry, you're gone. Compounds and elements, those are pure substances. Totally different ball game, right? So if we go back to A and B, we know in solutions, the particles there are 1 nanometer or less, right? They're pretty small and they don't scatter light when you shine a flashlight on that particular solution when it's in a container, like a clear container. But on colloids, yes, indeed, that's the medium-sized particles. Those are what, 1 nanometer to 1,000 nanometers. That will produce a Tyndall effect. Don't forget, last but not least, we have suspension. Suspensions are anything 1,000 nanometers and over, and you can mostly see them with the naked eye. So B is going to be your option here. We'll go ahead and circle that. If we move on to the next question, which mixture contains particles large enough to settle out over time? Aha, we just talked about that, right? So if we look at our options, we have A, solution, B, colloid, C, suspension, and D, homogeneous mixture. Now, A and D are kind of one and the same. They're cut from the same cloth. A solution is a type of homogeneous mixture. Remember, homogeneous is just generally same throughout, and you can't see distinct components of that mixture. And then colloid is very similar. The only thing is with colloid, the particles are a little bit bigger, and they'll scatter light. They'll show the Tyndall effect. So our only, of course, option would be C. So these are out. Solution and homogeneous mixture, those are the same. Colloids have the medium-sized particles, but suspensions have the larger particles that will settle out given enough time. Okay. Salt water. Salt water is best classified as, and the following options we have are suspension, colloid, solution, and compound. So if you remember from the discussion we had on the types of mixtures, and we can of course eliminate compound. That's not a good one. The actual salt itself is a compound, but when we put salt and water together, it's actually a solution. And the best example I can give you of that is, I remember when I was a young girl, I had a sore throat. I could put some salt and water, mix it up, and gargle with it, okay? And once you put that salt, or even sugar, I think we had an example of that earlier, you can't see, the substances dissolve, and you can't see the water that's hydrated those particles. So solution is your best answer there. Salt water, sugar water as well. Those are both solutions. Now, when we look at, we'll stop with this question here. Which of the following is a pure substance? And our options are air, milk, salt. We have NaCl. I'll go ahead and expand this out a bit. Okay. So, pure substance. So one of these guys is a pure substance, which we know pure substances are going to be an element, I can spell, or a compound. Okay, so elements could be like argon, O2, that's oxygen gas. This will give it away right here. NaCl, that's our common table salt. Okay, sodium chloride, potassium bromide. These are all ionic compounds and so on. Oh yeah, H2O. H2O. I can't do subscripts on here, unfortunately. CO2. Okay. Those are all compounds. They're either elements or compounds, right? So I'll separate these two. These are compounds. These are elements, okay? These are compounds. All right. So when we look at the options here, air is actually a mixture, and I talked about that a little bit in the video where we go over, pure substances and mixtures. Air is actually a mixture of O2, oxygen, gas, nitrogen gas. Those are the two main ones. Of course, we have carbon dioxide and CO2 and so on. Oh, okay. Milk. Milk is actually a mixture. It's a colloid. Okay, we talked about that in the video where milk, that one can be tricky because it looks consistent throughout, when you pour a glass of milk, but the actual particles itself in the mixture are bigger than, say, dissolved salt or dissolved sugar. Those are itty bitty. We're talking, again, less than a nanometer, whereas the milk, the particles in milk are going to be a little bit larger. That would include like the milk proteins and stuff like that. The main constituents of milk. So that's going to be, again, a colloid. I'll just go down here and say colloid. Not a cloud, colloid. And then I sort of gave away sand and water. Sand and water, that's going to be a mixture of, and it's going to be a suspension. Okay, sand and water, because you can see the particles and eventually the sand is going to settle out. If it's like if you mix it up and then give it time to settle, gravity's going to bring that sand down to the bottom of your container. Salt, there you go. That's a compound, okay? And that would be a pure substance. So if I go up here, it's going to be our compound. And it's a pure substance. Okay. It's right there. Boom. All right. So C is the final answer on that one. Which of the following is a pure substance out of those options? It's going to be salt or your NaCl. Moving right along. We have a student wants to test how the amount of sunlight affects the growth of tomato plants. And she sets up an experiment where each plant has a different number of hours of light per day, but we keep the water and the soil and the temperature the same. What is the independent variable? Okay, so we need to remember we have two types of variables in an experiment. We have the independent variable, which is the content that you change, the part of the experiment that you change to see if there's an effect. Now that effect would be measured as the dependent variable. So here, just to cover dependent variable, even though they're not asking, but if they did ask, you would say, well, it's the growth of the tomato plants. We would most likely look at the height or the size somehow of those tomato plants. Now the independent variable here is basically what are we changing? Well, keyword here, I see different number of hours of light per day. There you go. You're looking for a change, different number of hours. We're definitely going for hours of sunlight. Okay, so that would be option C. Soil, water, and temp, those are all the same. Those are controls. Those are just simply things you keep consistent or constant over the experiment. That way you don't have any confounding, we call them confounding variables, where they can sort of muddy the waters in your results, and you definitely don't want that. So C is your final answer there, hours of sunlight. The next question is going to ask, what step of the scientific method involves making an educated guess to explain an observation? So if you tuned into that video, we talked about the scientific method, and our options would be conclusion, hypothesis, experiment, or analysis. We have these four, and probably order them from beginning to end, or sort of in a stepwise timeline. But the first thing is ultimately you have to make an observation, right? So I would say if I were to do like a text, yeah, one, you do observation, right? Two, you would make your hypothesis. Three, you would do your experiment. And four, you would analysis and conclusion. If you look at like your general layout of lab experiments that you do, in general, you have like an introduction that explains why you're doing the experiment, maybe to settle an observation of some sort. It really depends. There's so many experiments you can do in chemistry. But in general, you come up with your hypothesis based on observations. You run your experiment, make sure you can, you document very well so it's reproducible and easy to replicate, as we talked about. And then, of course, your analysis and conclusion is basically going over the data that you pulled from the experiment and any conclusions you can make. And of course, we always talk about in lab reports, what can you analyze further in future experiments? So there you go. Final answer would be hypothesis. That's your educated guess. Which SI base unit is correctly matched with the quantity it measures along with the abbreviation? So basically, these are all mismatched, and you just need to pick the right one, the right one. That liter, like for instance, we have liter with an L, but liter measures volume. So A is clearly out of the picture. Mole, M-O-L-E, or M-O-L, that's an abbreviation for moles. That does truly capture the amount of substance. So I'm going to put a star there. Always check the last two just to make sure there's not a better answer. So when you're running through a test or taking a test, I mean, A might be an obvious and good answer, but simply make sure B, C, or D are not better answer options. Just a tip on test taking. Kelvin is actually a temperature, a way of measuring temperature of a substance. However, that's in K. Okay, that's just K, not kg. So that's sort of a distractor to see if students might pick that. And then meter. Meter is actually abbreviated M, and meter is going to do your distance. Okay, not time. Okay, so that's totally mismatched in multiple ways. So yes, mole, which is amount of substance. Okay, continuing on with the next question, we have a student who takes several measurements that are very close to each other, but far from the true value or accepted value. And an example, we'll go ahead and do an example here. I'll type in what I think could be an example of the scenario. So say like we measure, I don't know, a string, and we end up saying, okay, the accepted value is 10 centimeters. Wow, can I spell today? It's accepted value. But say a student comes along and it measures, he or she measures it, like for instance, 9.1 centimeter, maybe 9.0 centimeter, and 8.9. So they're very close to each other, right? They're very close to each other, but not really close to the accepted value, right? So we would say this is, it's not accurate, right? It doesn't match, not accurate, but precise, meaning that person replicated, that person did it 3 times and got pretty darn close. 9.1, 9.0, 8.9. Those are relatively close to each other, but they're not accurate. They're not close to the accepted value. So we just need to look for an answer option that matches that. So not accurate, but precise. Yeah. So option D says precise but not accurate. That would be the best answer choice. If we were to change it up a bit and say, hey, what if I said, all right, 8.9 centimeters. If I just said 8.9 centimeters is the accepted value, and the student came in and got 9.1 centimeters, 9.0, and then 8.9 centimeters, I would say, again, this is slightly objective, I would say that this would be an accurate and precise situation. These measurements are both precise. but they're repeatable and they come up with the same result time and time again. That's precision. Accurate just means how far or close you are to the target. Well, that's pretty close, pretty darn close. 8.9 was actually one of the measured values, and it's also the accepted value. So that's just a recap on how to do precision and accuracy. And this question we did right here is so common. I see it all the time in this particular section. Here we have, they just want you to convert 145 millis or milliliters to liters. Now in the video, when I did metric conversions, I used the chart, okay? And this would be where you start at the base unit, or sorry, no, you would start at the milli, right? And then you're moving over to the base unit of liters. Liters is represented by L. Oops, I'm on text still. Sorry. Yeah, this is L, right? So I'm going to show you the way of applying a ratio in order to get to the same answer. So if I start with 145 millis and I want to get to liters, okay, so my final answer will have liters. I'm going to apply the ratio of knowing that 1 liter has 1,000 small milliliters. Now you can actually write out 1,000, or you can write out 10 to the third. In fact, I will just write that out as well. 10 to the third. 1 times 10 to the third millis. Okay. And here I just say show your setup and include units in every step. So of course, yeah, when you do conversions, it's good dimensional analysis and conversion hygiene to put your units, and that just prevents you from putting the ratio in the correct order, or prevents you from doing it in the wrong order. And here I just confirm, yes, if I cancel my millis, I'm left with liters. And I'm simply taking 145 and dividing out by 1,000. Or yes, you could simply say, 10 to the third power, and you get 0.145. You can also move your decimal place to the left 3 times. You'll get the same exact answer. Okay, so 145 liters. Okay, yeah, and I don't know what this is. Could be a liquid, could be a gas. We don't know. But a lot of times in the gas unit, you'll be given, it's not uncommon to give you something in milliliters and you have to convert to liters. And also in solutions, they might give you something where a substance where you have it millis and you need to change it to liters. Millis is just short term for a shorthand term for milliliters. Okay, so again, ml and liters, those are very common in solutions and in your gas laws. And I'll leave it at that. And the next one is converting 3.75 inches to centimeters. We'll go ahead and start off with our given quantity. And we're given the fact that 1 inch is equivalent to 2.54 centimeters. And yeah, again, our final answer should be in centimeters. Okay, so if we cancel our inches, those are gone, top and bottom. We call it cross canceling, and we're just simply taking 3.75 times 2.54. We'll probably have to round 9.525. And if you want to put it into 3 significant figures here, we could just bump that 2 up to a 3, so 9.53 centimeters. If I'm doing a multiple choice exam here, I'd be looking for 9.53. Okay, so the next question is they want you to convert kilograms down to grams. So this is another, what we would call a metric conversion type question. So we're asked to take kilograms to grams. So on the chart that I showed you before, The larger units are on the left, so we're going from left to right. So we're moving our decimal point to the right. But I will show you the version where you simply indicate how many, if you have 1 kilogram, you have 1,000 grams, okay? Or 10 to the third. You can say it this way too. Wow. Okay, so your calculator will generate the same answer. No difference here. So we would say 0.825 times 1,000. We should get 825 grams. Oops. Oh, okay. I think I'm leaning my arm on this and it's causing problems. Okay. Yeah, and if you take 0.825 and then yeah, if you take 0.825 times 10 to the third power, you'll get the same answer there. 825. Okay. All right. And before we move on, I did indicate in the video that holistically, there would be 3 methods I would show you for doing metric conversions. So I showed you on the chart, right? You just move your decimal point left and right based on where you start and where you end up from a metric prefix perspective. Now, I showed you the method of where I take the larger unit and I break it down into several smaller units. So let me back up here real quick. So we'll do a comparison, and you can see and make the decision how you want to do these conversions. I always, when I'm working with the chemistry and physics students and so on, I make sure they understand, okay, you can do a metric conversion this way or that way, or use the chart, like do what feels right for you. So in essence, what I'm saying is the original problem I said, okay, I have kilograms, and I know 1 kilogram has 1,000 small grams. Okay, and that results in 825 grams. Okay, so we just did that. Now I could reverse it and say 0.825 kilograms. I could say 1 gram is 10 to the negative 3 kilograms. I'm just reversing my thought process on the fact that instead of saying the larger unit, 1 kilogram has 1,000 smaller grams, or I could say the 1 smaller gram is equivalent to 1/1000th of a kilogram. Okay, that is your third option. I see students do that. It's totally fine. What happens is dividing by 10 to the negative third power is the same as multiplying by 10 to the positive 3 power. The math, it maths out, okay? And I'm not trying to be, confusing in any way, just demonstrating that you could, because I honestly think some students might say, hey, Angie, why aren't you showing it this way? And again, it's because I have a personal preference, but you can do it however you want. Yeah. So when you take 0.825 and divide out by 10 to the power of negative 3, you end up with 825 grams. Okay. So to me, it's 6 one way, half dozen the other. It doesn't matter. For me, and I'm just going to put a big old star right here, it's easier for me to say 1 larger unit has a bunch of tiny units. It's very, very intuitive for me to say that and think that in my brain. But I could see if you want to use the alternative where you say 1 gram is 1/1000th, or, equal to 10 to the negative 3 kilograms, that'll get you there. I just think I try to avoid using negatives at all costs if I can, whether it's a negative exponent or a negative number. I just try to avoid that. So anyway, that those are my 2 cents on these two different methods. And again, you can use the chart too. Again, using the chart means that, of course, you have to me, if I were taking the test and just wanted to list those maybe prefixes on the top of my test, so I have it available and I can keep track of how many powers of 10 I need to go left or right. That's an option there too, but it really doesn't matter. You have one of those three methods. Again, this method here, number one, this method here, number two, or you can simply use the chart like I taught you in the video. All right, let's move on. We have a few more conversions and then we'll move on to the next topic. So we have 4.6 hours to seconds. And sometimes you can do, sometimes you have to apply multiple ratios here. So 1 minute has 60 seconds. Now, a lot of people know, and I think I had, down here, if you look down here, 1 hour is equivalent to 3,600 seconds. That's, 60 times 60 is 3,600, right? But we'll do it the long way. And ultimately, I end up with 4.6 times 60 times 60, 16,560. Okay, that's seconds. I'm not going to mind my significant figures here. Ultimately, I would say this is probably 1.7. Yeah, I would say if I wanted to mind my significant figures, this would be 17,000 seconds. But I'm not going to worry about that. What's important is that you know how to set up your conversion ratios and you get from the given quantity to your goal quantity. Okay, so we have 5.2 miles to feet in the next one. And I know 1 mile is just over 5,000 feet. So 1 mile is equivalent to 5,280 feet. So really it's just 5.2 times 5,280. I get 27,456 feet. Okay. That's up there. Almost 30,000 feet. Okay. Yeah, that's like plane altitude, I guess. All right, so this one, I threw this in because it's a little bit tricky. We have inches cubed to centimeters cubed, and that is a three-dimensional conversion, not a one-dimensional. So we just need to keep in mind this is a one-dimensional ratio, right? So I actually need to cube it in order for it to be useful here. So what I'll say, I'll start off with is 12.3 inches cubed. And 1 inch and 2.54. So notice, these units right here are, one-dimensional. I need to cube that entire quantity. So in essence, okay, so 1 inch cubed and I don't like what I did there. Okay, yeah, 1 inch cubed. Okay. So rules of exponents here, we are cubing both the top and bottom. Ultimately, what we end up with is 12.3 inches cubed. On the bottom, you have 1 inch cubed. That's just 1 times 1 times 1, or 1, and 2.54 cubed to the third power. That's 16.387. And I'm running out of room. Okay, and you cancel these units just like you would in any other, it's just a three-dimensional setup here. So I'm taking 12.3 times 16.387. Let me make sure I have that right. Oh. Yeah. times 12.3, I get roughly 201.56. You know, and I can say that's roughly, if I were to use 3 sig figs, again, I'm not concerned with or addressing it, but I could say that's 202. Be good with that. Okay. So remember, the conversion factor they give you is not it's not cubed, right? So you just have to cube it and then cancel your units and move on and carry out the multiplication. 55 miles per hour. So I'm just going to put miles per 1 hour because that's what that means, mph, miles per hour. I travel 55 miles in an hour's worth of time, right? And I want to go meters per second. And luckily, you know, they do give us the conversions here. So this just requires, you know, at least, you know, we have to change the top. We have to convert miles to meters and then hours to seconds. And that would entail back-to-back conversions, and you can just line them up. We call these train tracks. And we see that in future topics in chemistry where we do reaction chemistry and figure out how much product we'll get using conversions. But back to the 55 miles in 1 hour, I would start with, I mean, it doesn't matter which unit you convert first. This is multiplication, right? Order doesn't matter. And I can say 1 mile is equivalent to the 1609 meters. And because I want seconds on the bottom, I would put the 1 hour on top here with the 3600 seconds on the bottom. And you can cancel out all your units and make sure, okay, you know, hours are gone. And I circle meters per second. Hey, that's what I want. That's what the question asks for right there. So I simply need to take 55 times 1609 and divide out by 3600. That'll give us 24.5, what to say, 24.58 meters per second. And if we were to round, I mean, you could say 24.6 would be your final answer. Approximation. Okay. And the rest appeared simply to be metric conversions. And I'll present these as simply starting out with the given quantity and then using the larger unit with the several smaller units. That's easier for me. Again, you can pick your method. So 1 kilometer has 1,000 meters, or you could say, you know, 10 to the 3, doesn't matter. 4.5 times 1,000, 4,500. Okay. Okay. So 4.5 kilometers is equivalent to your 4,500 meters. And these are typically, I mean, you could see conversions like, well, like I had in the video, it was like megameters to micrometers, or no, it was megameters to nanometers. I mean, it was a really huge swing, right? And they might do that to test your skills, right? However, in chemistry, we're typically negotiating milliliters to liters or grams to milligrams, milligrams to grams, right? We're not going that, you know, 10, 12 decimal place conversion, right? I guess the only exception I can think of would be perhaps when you're dealing with wavelength, right? Because that's in nanometers. That's a very, very tiny unit you deal with in the electromagnetic spectrum, and then also maybe atomic radius. Though you don't even touch that until Gen Chem II. So anyway, just a note, just an observation, just something chem students should know. But when we go to the last few problems here, so I'm setting up 0.082 liters, and 1 liter is equivalent to 1,000 millis. We'll end up with 0.082 times 1,000. This should give us, no, excuse me, 82 liters. Or sorry, millis. Whoa, millis. Yeah. Remember what I said about, I think I mentioned this in the video, always take a step back and look at your answer and make sure it makes sense. And I caught my mistake because the original question was 0.082 liters and I gave 82 liters. I mean, that's like an oops, like write me a chemistry ticket for that one, right? That's, it happens. It happens. Your brain gets on autopilot and you pick the wrong unit. But anyway, we're down to, let's finish this 250 milligrams. And so milli, that's 10 to the -3, right? And it's on your chart. If you're referencing the chart I gave you, that's 3 decimal places. Let's see here, to the right from grams. But we're going from milligrams to grams, so we're going left. But be that as it may, 1 gram has, remember those are tinier units, so we know 1 gram has 1,000 tiny milligrams. Okay. And if we take 250 and divide out by 1,000, we'll get 0.25. Yeah, 0.25 grams. Okay. Okay, moving on to the next section here, we're going to do some review on scientific notation and significant figures. Now, it says here, write this, what we would call a standard or ordinary number, 0.000472 in scientific notation, and then, of course, include the correct number of significant figures. You shouldn't be losing any sig figs when you jump from one notation to the other. But what I'll do here is just simply determine, how many decimal points do I need to jump to jog down to where I force that number, the coefficient, to be between 1 and 10. And that would land me 1, 2, 3, 4 times. I'm going 4 times to land over at 4.72. And because I'm taking 4.72 and making it into a smaller number, I need to make this a negative exponent, okay? There are a couple different ways you could remember how to make this notation, but do realize that you are technically moving 4 decimal places over to the right to land, to make that coefficient a. Remember, it's a times 10 to the n power, right? This a has to be less than 10, right? So I can't make it 47.2. That's bad form. I have to make it 4.7. And, in essence, I moved it 4 spaces, but to correct the direction, right? Because if I were to move back, right, if I'm to take the scientific notation back, remember that negative exponent means I need to go left. Negative, left. That's pretty intuitive, right? On the number line, you go right to go positive, left to go negative. And so, yeah, and you can always, test yourself. Did I go the right way? 472, yeah. So if I start here and go 1, 2, 3, 4, yeah, you bet. I have 3 leading zeros, and then your 472. So this would be the correct answer. And of course, we have in the original number, we do have 3 significant figures, and 4.72, or 4.72 does have 3 sig figs. So we're good. All right. And we can take a standard, or sorry, we could take a scientific notation number and just move backwards and put it into standard decimal notation. We also call that ordinal. And we would say 6.02. And we're moving the decimal place 5 to the right. We're making this number bigger. So we have a positive exponent. So we would say 1, 2, 3, 4, 5. Now, I don't like to leave an answer like this. I would clean it up and say this equals 602,000 units, whatever that might be. We don't know. But 6.02 times 10 to the 5th power is, in essence, 602,000. Just checking on my calculator. How many sig figs do we have here? Well, we have 3. And we do have 3 here as well. The 602, remember those 3 zeros after the 2. Unless there's a decimal place, unless I put a decimal right here, we don't count those. And that's not implied at all. You actually have to see that decimal place. Your teacher has to put it in there, or the book, or the online homework. Okay. Let's see here, 3 sig figs. Okay, so we have 0.00894,321, and they want us to just round it off to 3 sig figs. So we can look at, I'm just going to write this number out. And in order to write it as 3 sig figs, remember these don't count, right? These don't count as sig figs. So really what we're looking at is chopping off our numbers to the right of that dashed line. And we'll just say that's approximately 0.00894. Now the three right there, remember if it's 5 and above, you give it a shove, but if it's 4 and below, just let it go. I just made that up, but that's, that 3 there means we don't round up. So we would simply say that's 0.00894 is your final answer. And these 3, we're just identifying how many significant figures do we have here. So looking at the first one, we have 0.00450. Trailing zeros do matter as long as there's a decimal point to the left. So we can count all 3 here. That would give option B as the correct answer. And same here, when we look at 120.30, we have a trailing zero that we would count because it's after the decimal point, and we would count that sandwiched 0. So I count 5 here. It's impossible to be 6. Some of these you can eliminate, right? Always eliminate when you can, right? Cross it off, and so you don't have to look at it or be tempted to answer it. Here we have, in scientific notation, you're just looking at your coefficient and determining how many significant figures you see here. And we would include these 2 zeros. We have a trailing 0 and a sandwich 0. So I count 4 total. And with addition, you simply have to line up. And then remember, addition and subtraction is all about placement. So every decimal place that's not in common with the other needs to go away. Doing that dashed line and trimming out that hundredths place will ensure that you don't report it. So when you do the addition, okay, so we get, I'm just going to do it on the calculator real quick. And I'm sorry, there's a snowblower outside. Yeah, 16.86. We would, because this is a 5 and above, give it a shove, right? We would make that 16.9. Yeah, this would be wrong. This would be wrong. Here we're adding. You know, it has to do when you're adding or subtracting, the decimal place matters, and it's all about how many decimal places you report, right? Each number has 3 sig figs, right? But here it's about placement. We're going to report out to the 10th place. Yeah, 16.9. Now here, if you're given a simple multiplication, you can just carry it out on your calculator. But remember, you just have to round accordingly because this answer gives me 4 sig figs, but you need to take a look at your problem and make sure, okay, I have 3 here and 2 here. I have 3 sig figs on the left and 2 on the right. I have to report the lowest. Okay, so 7.224 is not a good answer. And these aren't good either. You know, we just need to round it to the nearest tenths. So 7.2. That 2 in the hundredths place, that's not 5 or above, right? So we'll just leave it at 7.2. Okay, guys, we're on the home stretch here. I'm going to try and power through these last 2 pages as fast as possible without hopefully losing anybody here. Now, the first question asks, which particle determines the identity of an element? And that's just something you have to know. You have to memorize that. Protons identify an element. And back to the review, when I reviewed the section on the video, if I have an element that has 6 protons, by good golly, that's carbon, period. Nothing else. Nothing else. So a proton would be your first and the actual final answer. Of course, always scan to make sure there's nothing better. I don't see a better option. We have neutron, electron, and simply nucleus. Okay, that's funny, but no, those are not good options. So yeah, A is your final answer. Which statement correctly describes the mass number? So remember that mass number, that's going to be, let's see, A and Z. And so this is your generic setup of isotopic notation. A is your mass number and its protons and neutrons. Remember that protons and neutrons are in the nucleus and they contribute to the atom's mass. Electrons contribute to the volume or size, okay? Z is your atomic number and number of protons. So that's not the question at hand. It's mass number, okay? This is mass number and this is atomic number. And we're looking at mass number. So what's our answer here? Yeah, it's not number of electrons, not number of protons only. That's your atomic number. Okay, I like this. C is a good answer. Neutrons minus electrons, that's just nothing. It's a distractor. Sometimes you'll get a bogus answer option that you just have to say, I don't know what that is. It's not real. It looks like it could be, but it's not. Okay. An atom has 15 protons, 16 neutrons, 15 electrons, which is true. It has a -1 charge. It has a +1 charge. Well, in order for us to even look at these, we need to compare protons and electrons. Like, we need to do a comparison. Is one bigger than the other? And if we have more electrons, it's negative. If we have more protons than electrons, then it's positive, right? But when I look at, 15 electrons, 15 protons, that's like adding a charge of +15 and -15. That's a net 0, right? So I'm going to take off A and B. Neutral. Yes, it is neutral. It's at 0. Which just makes sure D is not better. 31 electrons, no, because, we explicitly say right here, 15 electrons. Maybe they're thinking you're going to add neutrons and electrons, but that's, again, it's a distractor. Yeah, we have a neutral atom here. So here's a very typical question here on giving an isotopic notation, tell me number of protons, neutrons, and electrons. And we can assume this is neutral, right? That we have a net zero charge. That's a way to say that. Just put the little zero superscript. But that's implicit. It's implied. Now, number of protons, that's easy button. That would be, again, I'm going to put A and Z, right? So that's our protons. And this is protons plus neutrons. Okay. Now, 13, yeah, so protons. And that P plus is just shorthand, right, to save my hand some stress, because I don't want to write out protons. Neutrons. So neutrons, again, that would be, that's A minus Z. Okay. A minus Z would give us, remember, A is protons plus neutrons, and Z is just the number of protons alone. So if we subtract them, we'll get the remainder would be our neutrons. So 27 minus 13, that's 14. Oops. Okay. Last but not least, electrons. That's the same as protons, and call it good. 13 protons, 13 electrons, since it's neutral, and 14 neutrons. Good to go. All right, so potassium here does have a +1. Remember, plus and +1, it's same thing, right? It's implied that when you see a plus, that's the same as this. Or if I see this, that's the same as that. Okay, they're interchangeable. All right, so protons, 19. Neutrons, that's Z minus A, and that's 40 minus 19, that'd be what, 21. And, electrons, we've got to be careful here. Ultimately, I know that I should have one more proton than electrons to have a +1 charge. So I'm just going to subtract 1 from 19 and get 18. So ultimately, we have 19 protons, 18 electrons to get that +1 charge, and then we have 21 neutrons. And that's the end of the story for potassium. Okay. K is a symbol for potassium. Okay. Which formula gives density? Okay. So this is just knowing that density equals mass per unit volume, or mass divided by volume. So I want to find something along that line. A is just flipped around backwards. No, it's not. Density is not a product. It's a ratio. This is meant to confuse you. I think this would end up, no, yeah. This is another distractor, right? 1 over mass times volume. That's not even, yeah, ew. Yeah, I don't think that's even a technical definition in any sense of chemistry or physics. And we're looking at finding the density. So they want to know the density given, given mass of 45 grams and a volume of 5.00 cubic centimeters. And so if we know the definition, we have the proper information here. We would just take 45.0 divided by 5. And notice both mass and volume have 3 sig figs. We can just keep it at 3 sig figs. Yeah, I get 9.00, yeah, grams per centimeters cubed. Sorry, my pen. I think what I'm doing is I'm leaning on the board here, and it's seen with my writing. Okay, grams. Okay, 9. All right. None of those options really look viable. 225, that's huge. That's probably 45 times 5. Yeah. So the other answer options sort of take into account maybe you'll reverse reverse things like option A um, is 5 divided by 45. Option D is if you take 45 times 5, and then option B, I mean, that's really just nothing. Taking 45 and dividing by 10. Yeah, so these are not viable options. Ultimately, you're looking at 9 grams per centimeters cubed. Okay. Which statement about water is true at typical room temperature? So remember, room temperature, it's 1 gram per milli, 1 gram per milliliter, or 1 gram per centimeter cubed. Okay, so I'm on the hunt for something that agrees with those statements. So remember, water has an assigned density, and that's an accepted value in chemistry of where 1 gram of water is equivalent to 1 milli of water in volume, and a 1 gram of water at room temperature is equivalent to 1 centimeter. And we kind of look at it like this, or 1 gram per 1 milli, 1 gram per 1 centimeter. You know, love 1-to-1 ratios, because if I say I have 20 grams of water, that means I have 20 mils of liquid water. It's a nice even ratio. Now, the one that sticks out to me is option C. I'm going to circle that. All the other ones, it's not a 1-to-1 ratio. Yeah, C is saying I have 1 centimeter cubed of water has a mass of 1 gram. And equivalently, we could say 1 liter or 1 milliliter of water has a mass of 1 gram. D, water is dense, more dense than most metals, does not make sense. I mean, you have a cup of water and you drop a metal, the metal's gonna sink. And that means the metal has more density than water. Um, and yeah, of course, A and B, 1 milli of water. I'm looking for 1 gram. And then they say 1 gram of water, it should be 1 mil. Yeah, so A, B, and D, those are bogus. Not good. Okay. And the rest here, it's like more density. A liquid sample has a mass of 32.5 and a volume of 26. Okay. Grams per milli. And they don't specify, what to give the answer in. I would, grams per milli, that's very common. I would take 32.5 and divide out by 26. And lo and behold, that just gives 1.25. Block of material does have a density of 2.70 grams per centimeters cubed and a volume. Make sure these match, right? Throw in some extra non-workable unit here. They want the mass, yeah. So again, we know density, or I'll use big D. Big D is mass per unit volume. We could simply, there are multiple ways of doing this. I'm just going to do it the classic algebraic approach where we just say 2.70 equals mass M, and we do know the volume of 15. And when we use our algebraic methods, 1 times M is just M if we cross multiply, and we take 15 times 2.70. Okay, so M is just a product of D and V. And we get 40.5 in grams, right? Because that mass is reported in grams. If they specify, hey, put it in kilograms or something like that, we would, of course, say, okay, well, 1 kilogram has 1,000 grams, and answer accordingly. However, that's, just watch for that. That would be 0.0405 kilograms. And I'm simply throwing it out there because you never know. Okay, we have a gas. Again, this is just a density problem, except we're doing gas here. So mass per unit volume. All right, gas has a mass of 0.882 grams and occupies a particular volume of 1.50 liters. And that is just using the definition of density, mass per unit volume, 0.882. Now, since it's a gas, you should probably have a lower volume. Okay, it's less than 1. And just make sure, yeah, in grams per liter, mass is in grams, and then volume is in liters. So we don't have to worry about converting. This is 0.588 grams per liter. Okay, our last section here is working with Kelvin and degrees Celsius and so on and so forth. So the first two questions ask for us to convert Celsius to degree Kelvin and then Kelvin degree Celsius. And then last but not least, we just have a Fahrenheit to 2 degrees Celsius. And we'll go ahead and complete these calculations and we will be done with this review. So congratulations, you made it. I'm not sure how long this video is going to be, but I'm sure it'll be a good hour if you do it from top to bottom, from beginning to end. Now, degrees Celsius to Kelvin. So we do know that Kelvin is measured as degrees Celsius plus 273. To be more specific, it's 273.15. So I think college chemistry will probably make you use the decimals. Sorry. So we'll go ahead and add those 2 decimal points. And in essence, we're going to say Kelvin is 25 plus 273.15. That's going to be 298.15. This is a very common temperature. We see it a lot in the gas laws. 25 degrees is room temperature. So there you have it. Very common. Common answer. Okay. Now we're just going to go backwards here. Degrees. If we use this fundamental equation here, I can simply take Kelvin and subtract the 273 to get degrees Celsius. Okay, so I will do that right now and get 313 minus 273.15 equals something degrees Celsius. So 313 minus 273.15. Okay. These two questions are just simply converting Celsius to Kelvin, Kelvin to Celsius. Luckily, it's a addition, right? Either adding 273 or taking away 273. But it's a very common maneuver in chemistry and especially in gas laws and in parts of Gen Chem II. Okay, degrees Celsius. So we're taking Fahrenheit to degrees Celsius. And I forget the actual formula. Okay. Oh, yeah. So we already have Fahrenheit. We're trying to find Celsius. Okay. Yeah, so Celsius is, we just rearrange that. We'll take degrees minus 32 times 5/9. Okay. Sorry, it took me a while to find the right formula. So we're going to use this formula right here. Degrees Celsius equals, we'll take the difference of Fahrenheit minus 32 times 5/9. That's going to be 98.6. I think that's normal body temperature. All right, so mathematically, we come up with times 5 and divide out by 9. Yeah, 37 degrees. Our final answer there. All right, pin drop. That concludes this particular review, which covered, I think, my item count came to 50 or 51 problems.